Lesson 5. Transverse shear in beams. Last lesson, the bending moment made normal stress out at the fibers. Now the same load drives a shear force down the beam, and that makes a shear stress. 3 one-line ideas. Transverse shear stress is VQ over IB. The first moment Q is what carries the geometry, and the stress peaks at the neutral axis, exactly where bending stress is 0. Get those 3, and beam shear problems fall out fast. Here's the problem. Take a rectangular section, 50 wide by 150 deep, the same section as last lesson, but now it carries a maximum shear force of 30 kilonewtons. Find the peak transverse shear stress 2 ways. First, with the rectangle shortcut, then from the general formula evaluated at the neutral axis. The two had better land on the same number. Concept 1. Transverse shear stress. The internal shear force does not act at a single point. It smears a shear stress across the whole depth. Tau equals V times Q divided by I times B. The shear force times the first moment, divided by the moment of inertia and the width at the cut. But the stress is not uniform. It is 0 at the top and bottom fibers, and largest at the neutral axis. That is the exact mirror of bending, where the normal stress peaked at the outer fiber and vanished on the neutral axis. Concept 2. The first moment Q. This is the piece that trips people up. To find the shear stress at a level, slice the section there, keep the part beyond the slice, and take its area times the distance from the neutral axis to that part's own centroid. Q equals A prime times Y bar prime. At the very top fiber there is no area beyond the cut, so Q is 0. At the neutral axis the whole top half is beyond the cut, so Q is largest. For a rectangle, that maximum Q works out to BH squared over 8. Concept 3. The shortcuts. Evaluate VQ over IB at the neutral axis for a fixed shape, and all the geometry collapses into a single constant times the average shear, V over A. For a rectangle, the peak is 3/2 the average. For a solid circle, it is 4/3. The handbook tabulates these directly, so when the section is a standard rectangle or round, you can skip straight to the factor. Setup. Build the table. The shear force, width, and depth up top, then a blank with its formula for every unknown. The area, the first moment at the neutral axis, the moment of inertia, and the peak shear stress. Then commit to one unit system. I'll keep the shear force in newtons and the section in millimeters, so the stress lands directly in megapascals. The one thing to stage now is the shear force in newtons. Solve. Part 1. The shortcut. First, the area. Width times depth. Then, the rectangle formula. 3/2 times the shear force over the area. The average shear is 4 megapascals, and the rectangle lifts it by a factor of 3/2 at the neutral axis. Peak shear, 6 megapascals, one line. Part 2. The cross-check. Rebuild the same stress from the general formula at the neutral axis. The first moment of the top half is BH squared over 8. The moment of inertia is BH cubed over 12. The width at the cut is the full width. Feed them into VQ over IB, and it lands on the same 6 megapascals. That is no accident. With those two geometry terms, the formula reduces exactly to 3/2 V over the area. The shortcut is this cross-check, already solved. Final answers. Area, 7,500. First moment at the neutral axis, about 140,000. Peak transverse shear stress, 6 megapascals, confirmed both ways. And it sits on the neutral axis, the very line where bending stress vanished. Notice the average shear was only 4 megapascals, so quoting V over A alone would have underreported the peak by 1/3. Traps. 3 ways transverse shear bites. 1. Compute Q correctly. It is the first moment of the area beyond the cut, taken about the neutral axis, and for the peak, you take the whole area above the neutral axis. A wrong Q is the number 1 miss. 2. The peak is at the neutral axis, not the surface. Bending stress maxes at the outer fiber, transverse shear maxes at the neutral axis, where the bending stress is 0. So never evaluate shear at the top fiber, where Q is 0. 3. The width B is the width at the level of the cut. Full width for a rectangle, but the thin web thickness for an I-beam. which is exactly why webs carry the shear. Quick recall. Transverse shear stress is VQ over IB. The first moment Q is the area beyond the cut times its centroid distance from the neutral axis. For standard sections, use the shortcuts. 3/2 V over A for a rectangle, 4/3 for a solid circle. Golden rule: shear peaks at the neutral axis where Q is largest, and it is 0 at the top and bottom fibers. Next up, Lesson 6, Beam Deflection. We now have both beam stresses, bending at the fiber and shear at the neutral axis. But real designs are just as often limited by how far the beam sags. So next lesson, we turn the load into a deflection. The standard case is like P times L cubed over 48 EI for a central point load. Before then, redo today's section as a solid round under the same shear, and use the 4/3 factor. Everything's at peprepengine.com, cheat sheet, work solution, and a quiz attached here. If the course helps, subscribe.